Hi students, this is Dr. Dearden, and I'm, as promised, going to finish up recording the end of Chapter 11 of Physical Science 100. So, where we left off, we had just talked about the photoelectric effect, and what we found was you can't explain the photoelectric effect. Remember, that's where ultraviolet light can knock electrons off of a metal surface, whereas light that is longer wavelength, like visible light or infrared light, no matter how bright it is, can't knock the electrons off. This was explained by Einstein, and the bottom line is you can't explain the photoelectric effect if you think of light behaving like a classical wave. Because classical waves, if the amplitude is big enough, should knock the electrons off. But you can explain it if you think about light behaving like a stream of particles, where the energy of the particle is proportional to the wavelength of the, or not the wavelength, the frequency of the photons. If the frequency is high enough, if you have an ultraviolet photon, that's enough so that those photons interacting with the metal one at a time can eject electrons off the metal. But if you go to lower frequencies, the individual photons don't have enough energy to knock the electrons off. So you have to think of light as behaving like a stream of particles. So here's the quiz question we didn't have. It says the arrival of light is lumpy. So what do you conclude from that? Well, you could conclude A, Newton was right, light's made up of particles. That's what you'd want to conclude from it. You wouldn't decide that the experiments must be wrong somehow. We have observed what we've observed. We do know, however, that light diffracts and interferes, so it does have wave properties. Could you say, see, physicists don't know what they're talking about? We should study geology instead? Well, we're going to do that. And we could just listen to music, but we've got a dilemma. That's really what the bottom line is here. So what do we have to conclude based on the photoelectric effect experiment and the way that light arrives to make dim images, photographs? You have to decide that light is particulate. It is. But, again, that's a dilemma. How is it possible for a particle to make an interference pattern? And how is it possible for a wave to arrive and make individual spots? That's really a difficult problem. So how do we resolve this problem? Well, one more quiz. What is light? Is it particles, waves, both, neither, or Breyer's vanilla ice cream? Well, the obvious answer to this little quiz is it's Breyer's vanilla ice cream, the best kind of ice cream there is. No, what do? Well, we really need a new idea. And the new idea is the idea of wave-particle duality. So I have here a short video that's going to explain how photons can interfere. And in this video clip, what you're going to see is particles going through, well, it's the so-called two-slit experiment, where our particles, in this case they would be photons, go through these slits and they end up hitting a screen over here. And you're going to see that they arrive as little dots, the way particles would. But where the particles land is described by an interference pattern, and that's how we resolve this dilemma. So let me play this back. Hopefully it will record and you'll be able to hear it. So here goes.
Light passing through two slits causes an obvious wave interference, which clearly reveals itself as a pattern of light and dark stripes. There is no question about light being a wave. Only waves behave this way. So the question is, how can light be particles and still interfere like waves? If light is made of photon particles, individual little things which can't arrive as a spread out pattern, then each particle has to hit the screen individually. A single spot of light here, for example, another photon there. It's impossible to predict precisely where any spot will appear, but it is possible to see that more photons land in some places than others. In fact, there's a higher probability that more photons will land in certain regions. And eventually, because of those probabilities, the result will be a definite wave-like diffraction pattern of particles.
So as you saw in this movie, there are certain places where the particles land where there's a high probability of them landing. There are other places where the probability of them landing is zero and there were gaps. And that's how you end up with an interference pattern from individual photons arriving at different places on the screen. So this idea is a new idea. It's the idea of wave-particle duality. And stated succinctly, what it means is that our question to begin with of whether light is a wave or a particle is really the wrong question, because light is neither a wave nor a particle. Light is really light. That is, it's something that has the characteristics of both waves and particles. And the reason this is strange to us is that we don't see things like this in our everyday experience. And yet, in the world of quantum mechanics, this kind of thing is common. And I'll jump ahead and tell you that it gets stranger yet. It's not just light that does this. It turns out that everything does this. It's just that in most cases we see only the wave behavior or only the particle behavior. It's hard to see both at the same time, yet for some things we can. So, how do photons interfere? Well, if they go through two slits, certain paths are more likely than others. And which ones are likely are determined by the width of the slit and the frequency of the light, on how it hits the walls of the slits, that kind of stuff. The photons do arrive in lumps like particles, so they have particle behavior, but the probability of where they end up hitting when they get back to the detection screen is distributed just like the intensity distribution of two interfering waves if you're going through two slits. And that's the essence of wave-particle duality. So, electromagnetic radiation, when we observe it, is observed as particles. And the experiments that show that, and this is something we will test you on, although this is not on exam 1, it's on exam 2. The evidence is in the formation of dim images, the light arrives as little specks. It doesn't arrive as a dim image that slowly gets brighter. And the other bit of evidence for particle behavior is the photoelectric effect, which you can only explain as the photons being individual particles. But where those particles end up landing is described by waves, and the wave is really a wave of probability. And so it's because of that that we see diffraction patterns from or diffraction of light as it goes through a hole or encounters an object and spreads out. We saw that. And that's why we get interference patterns where you have multiple slits and the light from those two slits interferes, so that you get places where there's constructive interference with the waves of probability adding together, and other places where there is destructive interference with the waves of probability canceling. And that's the end. So that's what you need to know from Chapter 11. And we'll continue on with Chapter 12. As I mentioned last Thursday night, my daughter is going to present that. So show up and be nice to her. She'll do a great job for you. Talk to you later.